Alright, hey y'all, Mr. Kyer Myers Mathematics, and let's just jump into it. This is the first day of a new series. So we did a series going through numbers 1 through 30. Now we're on 31. So as we go, I'll probably just do series in that like galaxy color to represent the earlier 30, rather than writing 31 of them, because if you were following the last series, I was writing series over and over and over again, however many numbers it was. Anyways, let's go ahead and jump in. So we want to figure out if the sequence is bounded and whether it is eventually monotone, increasing, or decreasing. So it can either be bounded or unbounded, and then it can be monotone, and if it's monotone, then it can be increasing or decreasing. So let's look at what that looks like. We can actually figure out all of the answers to those questions with a T-chart. So if I do in, and then we'll call that whole thing a sub n. So a sub n is n over 2 to the n. Okay? So we're going to go like this, and like this, and like this, and like this. Okay, so n is starting at 2, it looks like. So we want to start at 2. Okay? Well, then that would be 2 over 2 squared, which I'll simplify kind of in the down direction, I think, would just be 2 over 4, which is 1/2. Okay, good so far. What about 3? Well, then that would be 3 over 2 to the third power. That's not going to simplify quite as much. Oh, I'm writing 2 instead of 3. Sorry. Other way around. 3 over 2 to the third power is 8. So it's going to be 3/8, and that's not going to simplify anymore. If we want to write these as decimals to figure out which is which, I mean, you can kind of just figure out which one is bigger. But as a decimal, it'd be even easier. That's going to be 0.125, 0.25, 0.375, I believe. I could be wrong on that. I think that's 0.375 as a decimal. So it seems like it's getting smaller so far. 4 over 2 to the fourth power. Well, 2 to the fourth power would be 2 squared squared. 2 squared is 4. 4 squared is 16. That's 4 over 16 is 1/4, which is 0.25. So it does seem like it's going down. So far, it has been going down. It's been monotone decreasing so far. And I don't see how it would stop with this pattern. There doesn't seem to be any point at which this pattern shouldn't keep going. And I have no idea what 530 seconds is. But it's probably less than 0.25, right? Because what would it be? Like 830 seconds would be a quarter? So that's going to be less than a quarter. Same thing for 6. That's 2 to the 6th power. So it's going to be 6 over 64. And notice the 2 is just going to go up by 2, right? It's like 4 times 2 is 8. 8 times 2 is 16, because that's a power of 2. And then on the top, it's just going to increase by 1s, because it's just n. So if the bottom is an exponential and the top is just a linear function, the bottom's going to infinity a lot faster than the top is, which means that as you go to infinity, it's essentially like 1 over infinity. And then that would end up being 0, right? So that's another thing that we'll talk about here in a second. So 530 seconds and then 330 seconds, right? So that's definitely less than 530 seconds. If the denominator is the same, you just compare the numerators. So it definitely is going down. And the thing is, we can kind of just skip to infinity now. If you need to show more work, you might show something like, you know, a sub n plus 1. You need to show that it's always less than, sorry, wrong sign, less than a sub n. And so if you need to show something a little bit more profound, maybe you could do something like this, where you would say n plus 1 over 2 to the n plus 1. And then that would be n over 2 to the n. Then this would be n plus 1 over 2 to the n times 2. N over 2 to the n. And remember what I was saying earlier about how if you have the denominators the same, you can just compare the numerators? Well, 1/2 of n plus 1 less than n over 2 to the n over 2 to the n. So we just get rid of the 2 to the n's at that point. So you're saying 1/2 of n plus 1 is less than n for all n. And for n values starting at 2 and greater, yeah. Now, if the n values got small enough, then no, but you're taking half and then just adding 1 back. So for any value that is 2 or greater, then that should work, because if I plug in 2 exactly, that's going to be half of 2. If I distribute, I could say it's 1/2 n plus a half. So it's half of 2 is 1 plus a half, right? Well, if you're starting at 2, then a half of 2 plus a half, you would end up just adding a half back. Whereas over here, if you're plugging in 2, it would just end up being a 2. So it's 1.5, a 1.5 versus a 2. And then it would just keep, that gap would keep increasing as you have n values that are greater than 2. So you might want to elaborate on that a little bit if your teacher is a little bit of a stickler. But that should be the basis for what's good enough, if that makes sense. I don't want to dive too far in, because for most professors, it probably would be fine to just use like a nice T-chart or something. So that would prove that it is decreasing, and also it would prove that it's monotone. So something like this would be a little bit more formal, but also the T-chart helps us to see that it is going down and it is monotone. If I go to infinity, what I'm doing is the limit, essentially, right? So the limit as n goes to infinity of n over 2 to the n. And I would just say that that goes to 0 because the bottom is going to infinity faster. But if you need something a little bit more substantial, you could use L'Hopital's rule, because you're plugging in infinity, so it's infinity over infinity. It's one of your indeterminate forms. So then we could say the derivative of n is 1, and the derivative of 2 to the n would be 2 to the n times the ln of 2. And then that limit would go to 0, because a limit as n goes to infinity of a constant over an increasing function is 0. So that you could just use that definition of infinite limits going to 0. And that should probably be sufficient as well. So what's happening? It's bounded because the limit is something. The limit could be anything, and then it would be bounded. And then it's monotone because it's always doing the same thing. And because it's monotone, it has to be either monotone increasing or decreasing. I guess it could be monotone stagnant, but you'll hardly ever see that. It's usually one or the other. So the final thing we would say here, it says for each of the following sequences whose nth terms are an indicated state whether the sequence is bounded and whether it is eventually monotone, increasing, decreasing. So I guess if we're going to go in order, we would say the sequence, and we'll call it a sub n since we called that earlier, the sequence. The sequence a sub n is bounded. And is, we would say, monotone decreasing. Monotonic. You could also say some monotone or monotonic. They said monotone, so it's really just how you guys want to say it. The sequence is bounded and is monotonic decreasing. And I believe that answers the question more or less exactly how they wanted us to. So I kind of hinted at this just earlier, but your teacher might want you to answer the question a little bit differently. They might want you to word it a little differently. I'm just trying to stick to exactly how they're wording it in the problem, because that's probably the safest thing to do. But if your professor is like, I want you to call it this, just go based off of what they wanted you to call it in the notes. Like, oh, it needs to be called bounded by this. Like maybe they want more information on how it's bounded. Or, monotone decreasing instead of monotonic decreasing. And they have some sort of profound reason for why it should be one or the other. It doesn't really matter, as long as you're communicating what you need to communicate. So that would be the answer, and hope that's been helpful. This is the first video since we took a break from the last set of 30. We're on 31, so we're going to go from 31 to 60. I'm going to do these videos in sets of 30, so all the months that have 30 days in them. That way it's just easy math for me to keep track of. I know it's ironic. The math teacher is trying to give himself easier math. But yeah, so just check that out, and check out the other videos that are in this series. That should be linked somewhere around as this video comes to a close. And speaking of other things and resources that you can check out, I have the 5 math mistakes everyone makes and how to avoid them. You can check that out at myersmathematics.com, and that link's in the description below. Catch you guys in the next video. Blessings, y'all.